you try to make these things as light as you can because they're reciprocating, but you still have to have some toughness to go with that. Let's go on to the stress-strain graph that's on page 3. And let's kind of talk through that a little bit. I've kind of alluded to some of this, and this is kind of two broad ways of looking at this. You can have 4130 steel that can be heat treated upwards of, on a Rockwell scale, which is a hardened scale, you could have it heat treated to 40 Rockwell. And at that point in time, you drop the chromoly on the ground and it's going to break too. It's really strong as long as you don't hit it with an impact. So that tallest part of the graph that you're seeing, if you're looking at this, is representing something that's been heat treated. But what you want to look at here is where that straight line starts to curve is where it's failing. And notice that the distance from where it started to fail to where it finally failed is pretty short. So that means that if you didn't plan for that, there's not a lot of safety factor in that kind of material. Now, the one that's showing up as 4130 condition N, which is what a lot of people build race cars out of, is showing that it failed sooner, but it stretched, and then finally it failed. Well, the area underneath that curve, again, shows the toughness of that material. It's how much total energy it would take until it actually fully separated. The failure point, or the so-called rupture point, is where it's no more. Everything is separated. You're hosed. And so with the condition in material, you've just got a huge amount of safety. I've given some definitions below. Ultimate tensile, again, is the highest point on the curve, and that's what, when you see Columbus or True Temper or Dedachai or whoever quoting a tensile number, that's the number that they're going to quote to you. That number without another number, which is called elongation, which we'll talk about a little bit here, is kind of meaningless because, again, you want to know something about what's this stuff going to do when you hit something. And without having this kind of either a graph or something that describes what this graph is, you kind of don't really know what the material is. Let's talk about work hardening a little bit. Work hardening happens in bicycle tubing a lot. The way you form butts on tubing is you take it cold and you stick it in a machine that essentially wipes material. Mark knows a lot about this. That wipes material and it gets the tubes close to red hot in the process, but it actually physically takes all of those sugar cubes of steel and it slips them along on each other, and as they slip, there are defects. In other words, well, a good illustration. 6-lane highway, cars rolling down it, a semi jackknife. All the cars start to pile up. Well, that's kind of what happens when you cold work steel, is you have this movement that's happening as you're starting to pull that steel apart and stretch it. But what also happens is defects in that steel at that granular size start to happen, and they start to bind up on each other like that jackknife. When they do that, that steel will not move anymore. And that's what strain hardening or cold working is. It's those defects causing a clog, or for lack of a better word, a car crash on the highway of this steel. So what happens is when that happens, that stuff stops, and then that stress has to go somewhere else and find that until the stress gets high enough to actually just cause that defect to separate. So this will become more important as we keep walking through this. So that's what cold working is about. If you go to the next page where it shows the sugar cane, I thought about doing this, I didn't do it, but I thought about bringing a box of sugar cubes. And what really happens in cold work is, if you can visualize taking this box of sugar cubes, 3 or 4 high by, let's say, 20 long by 10, if you can think of taking a popsicle stick and wiping it and taking one of those layers and moving it, that's what happens when you cold work. That's a kind of a perfect version of it. It doesn't happen quite like that, but that's actually what happens is the material actually moves along on what engineers or material scientists would call slippage planes. It actually will slip until it actually balls up with something else and then it will stop. So the thing that's important about this is that when those things are moving, it's compressing these bonds. These steel grains actually, I mentioned something about body-centered cubic. They look a bit like a sugar cube with another interstitial grain on the inside of it. And what happens is all these things are bonded together, and the bonds are like springs. So when you compress a spring, what happens? Anyone? It stores energy. It wants to spring back. What happens when you pull a spring out? It stores energy. It wants to go back. Well, that's the same thing that happens with steels at the micro level. Is as you cold work them, these bonds get compressed. They store energy, and that's one of the primary ways that the material gets stronger. So if you can control how much of that you're getting, you can do some really amazing things with steels in cold working, which is actually what the bike tubing makers do. Let's see, ductility. Yeah, one of the things that you always want is you want this balance. Cold working is great. That's this part where you're actually usually, this drops a little bit and then it can actually move up. It actually increases strength as those cellular things are crashing and they're getting stronger. What's happening is the car crash happened. Those things are moving. Those grains are starting to make those dislocations are starting to form, and you're starting to cause that pile up on the freeway. And at some point, it hits the maximum amount, and then there's a guy with a bulldozer that comes on behind it, and he pushes all the cars out of the way, and that's what this part is actually at some point, the steel will not hold any more force. It actually starts to separate, and it cross-sectionally starts to reduce. So engineers call this necking, but all it really means is it just means that the material has been pulled on enough so that it's plastically deformed, and now it's actually starting to reduce in size. It's getting weaker. So at that point, you know that the end is near, and the material is going to fail. Let's go on to the next page that's talking about air hardening, or it's actually about hardening of carbon. One of the easiest ways to make a steel harder is just to add carbon to it. It causes more blockage of the sorts that we're talking about here. The one thing it doesn't do is it does not increase ductility. It gets harder, ductility goes down. So if you want, again, cheap files, add carbon. If you want files that last longer and they're tougher, you have to add other things. Vanadium, used in tool steel, phosphorus. There are other things that you would add to try to make that steel tougher. Let's see, where am I at here? Oh yeah, hardness. We are the only people in the industry that are a distributor of tubing that actually test it. We actually have the capabilities to take samples from the manufacturers, and they tell us it's X. Well, maybe it's X and maybe it's not. We actually cut them, and we have a hardness tester. And if you look on the next page, there's an old grizzled guy who is doing a hardness test. And you see these rings of tubes that have been cut, and they've got numbers on them. Well, we actually check this stuff because we know that even if a manufacturer says that they have X tensile, which is their best number, we know that that can vary because, well, I'll give you an example. You take a tube and you're going to draw it. Well, out in the thin section of that tube, it started thicker and it got thinner. It got more cold work out in the middle of the tube than it did on the thick section. So in the absence of any other thermal treatment, that tube is going to be harder in the middle and softer on the ends. That's not a bad thing as it relates to bicycles, because you kind of want the dent resistance out in the middle, and frankly, most frames don't fail out in the middle. They fail close to the joints anyway. So that's not a bad thing. So we test, and we do it for diagnostic reasons sometimes. Maybe we see something that looks a little unusual, and we want to say to the manufacturer, hey, what changed here? Are you using a different supplier for your raw material? And that keeps manufacturers honest. So we have a way of kind of checking it. So we do.